Hello, I'm J.D. Harrington, Public Affairs Officer for NASA's Science Mission Directorate. I'd like to welcome you today to this news conference where we're going to discuss a new Hubble Space Telescope observation that allows astronomers to predict with certainty the next major cosmic event to affect our entire galaxy, sun, and solar system. Before we get started, though, a few housekeeping duties. We have 4 panelists joining us today. Each will give a short 3 to 5 minute briefing on their specific topic. Next, we will move to the question and answer session. Accepting questions from media here at NASA headquarters, those at the centers, and also those that dial into the telephone bridge. Questions can also be submitted via the Twitter sphere by using the hashtag AskNASA. The panelists will also host a web chat this afternoon at 3 p.m. to take questions from the general public. I'll give the URL later on in the presentation. This media conference will be limited to 55 minutes. Today's panelists include Roland Van de Marle, an astronomer at the Space Telescope Science Institute in Baltimore, Maryland, and the principal investigator of the science team that performed the study described today. Segmo Tony Sohn, the astronomer at the Space Telescope Science Institute in Baltimore, is also a key member of the science team. Next, we have Rosemary Wise, professor of physics and astronomy at the Johns Hopkins University in Baltimore, Maryland, and a renowned expert in the formulation and evolution of galaxies. She is not associated with the science team. And next to Rosemary, we have John Grunsfeld, NASA Science Mission Directorate, Associate Administrator in Washington, D.C., and 3-time Hubble repair astronaut. And with that, let's hear about our science finding today. Here's Roland.
Thank you so much, JG. Our sun resides in the Milky Way galaxy. We can see this in the first graphic. The Andromeda galaxy is the nearest big galaxy to our Milky Way in the universe. It is at a distance of 2.5 million light years, but it is one of the few galaxies that can be seen with the naked eye. Exactly 100 years ago, the Andromeda galaxy was the first galaxy for which it was possible to measure its relative motion with respect to us. As it turns out, the Andromeda galaxy is coming towards us at 250,000 miles per hour. This is unusual because we live in an expanding universe and almost all other galaxies are moving away from us. This measurement 100 years ago was obtained using the so-called Doppler effect, which is also used in many modern technologies, for example the measurement of the speeds of vehicles on the highway using radar. Because Andromeda is getting closer to us, astronomers have speculated for a long time whether it might collide with our Milky Way and whether the galaxies might merge together. However, to know whether this will in fact happen, it is necessary to know not only how Andromeda is moving in our direction, but also what its sideways motion is, because that will determine whether Andromeda will miss us at a distance or whether it might be heading straight for us. Astronomers have tried to measure the sideways motion of Andromeda for over a century. However, this was always unsuccessful because the available techniques were not sufficient to perform the measurement. We are here today to announce that for the very first time we've been able to measure the sideways motion, in astronomy also known as proper motion, of the Andromeda galaxy, using the unique observational capabilities of the Hubble Space Telescope. How we performed this measurement will be described later by my colleague Dr. Sohn, who is sitting next to me here. We find that to within the precision of our measurements, the Andromeda galaxy is heading straight in our direction. What this means is that the galaxies will collide and they will merge together to form one new galaxy. If we look at the graphic again that we showed before, you see that there is a third galaxy, the Triangulum galaxy, also known as M33, which may also be involved in this smash-up. So what this all means is that we can now predict with certainty the next major cosmic event to affect our entire galaxy and which will drastically change the environment of our sun and solar system. To calculate how these events will unfold, we perform detailed computer simulations of the future collision. This part of the project was performed by my colleague Dr. Besla, who is here in the audience today. And if there are any questions later about this part of our work, she will be happy to answer any questions. What we will show next is a movie of how the evolution may proceed over the next 8 billion years. If we can start the movie, you will see that we first see the Milky Way galaxy from above. Stars rotate around the center of the Milky Way on circular orbits. After about 1 billion years, the camera angle moves, so we see the Milky Way from the side. It is now clear that the Milky Way is a very flat galaxy, like a frisbee. As the camera zooms out, we see the Andromeda galaxy approaching us. The approach takes several billions of years because of Andromeda's great distance from us. But after about 4 billion years, the galaxies will have a direct collision or a very close encounter. The galaxies will get distorted, and some of the stars will be thrown out into tidal tails. The galaxies will also be slowed down so that they fall back together, which will lead to a complete merger of the two systems 6 billion years from now. If you continue to watch the movie, you will see that the merged galaxy will have a different shape. It has a more of a three-dimensional structure, and it is what is known in astronomy as an elliptical galaxy. We know of such galaxies in the universe around us, and many elliptical galaxies that we see might have formed in this way. You will also see that the galaxy appears redder owing to the fact that its stars are now older. Our measurements and computations show that the first passage does not need to be as direct a hit as shown in the movie we just showed. However, we do find that in all simulations we've run, the galaxies do ultimately merge together. We do know of other galaxies in the local universe around us that are in the process of colliding and merging, as my colleague Dr. Wise will describe later. However, what makes the future merger of the Andromeda galaxy and the Milky Way so special is that it'll happen to us. It will be our galaxy, our sun, our planet, and not some distant object in the universe. If I can have the next graphic, please. This shows how the environment of our sun will change. On the left, you see the sun currently moving around in a circle in a flat spiral galaxy, our Milky Way. This is how our sun was born 5 billion years ago, and what it's been doing ever since. After the collision with the Andromeda galaxy, the environment of our sun will be very different. Our sun will live in an elliptical galaxy, which is somewhat bigger and is also somewhat redder. Moreover, most likely the sun will find itself on a much wider orbit in this galaxy that takes it much further from the center of the galaxy. When Andromeda arrives here, the sun will still be a regular star with its planetary system as it is today. The sun will not run out of its nuclear fuel for another 2 billion of years after that. The distances between stars and galaxies are vast, so when the two galaxies collide, the individual stars will not actually run into each other. No individual star in Andromeda will directly hit our sun, and in fact, it is unlikely that any star would even come close enough to significantly perturb the Earth's place in the solar system. It is possible that 4 billion years from now, our or some other civilization may still be around. If so, they will witness spectacular and slow changes of the night sky. If I can see the beginning of the next movie, this will show how the night sky will evolve. The beginning of the movie shows what the sky looks like today. On the right, you see the majestic Milky Way galaxy. Because it is a flat galaxy that we see from the side, it appears to us as a luminous band on the sky. And also, just left of that, you see a small fudge, which is the Andromeda galaxy. If we can start the movie now, we will see that as Andromeda moves towards us, it'll get bigger on the sky, and it gets close enough to distort our Milky Way. As the galaxies pass each other, bright new regions of star formation will light up the sky as gas gets compressed and forms new stars. Over time, the gas and dust will be lost from the system, the star formation ceases, and all that's left will be a bright elliptical galaxy filling much of our night sky, having replaced today's familiar view of the Milky Way. Today, the Andromeda galaxy appears to us on the sky as a small fuzzy object that was first seen by ancient astronomers more than 1,000 years ago. Few things fascinate us humans more than to know what our cosmic destiny and future fate will be. The fact that we can predict that this small fuzzy object will one day come to engulf and enshroud our sun and solar system is a truly remarkable and fascinating finding. With that, I would like to hand it over to another member from my team, which, next to myself, consists of several other people. namely Drs. Sohn, Anderson, Besla, Fardal, Beaton, Cox, Brown, and Guarta-Curta. Dr. Sohn will describe how we used the data and the measurements to obtain these new results. Tony.
Thank you, Dr. Van. In the next few minutes, I'll describe how we used the Hubble Space Telescope to measure the sideways motion of the Andromeda Galaxy. Can I have the next image, please? The displayed image shows the Andromeda Galaxy covering a region several times the size of the full moon. And the small box indicates one of the 3 regions for which we took pictures with Hubble. Andromeda contains a halo of stars that extends well beyond the main disk-like body. So even though the box appears to be outside of Andromeda, it actually contains tens of thousands of Andromeda stars. The blow-up image on the left shows the actual view of this field with Hubble. In addition to Andromeda stars, the image shows many small fuzzy objects, and these are faraway galaxies in the distant background. As pointed out earlier, it has been known for a while that Andromeda is approaching us at a great speed, and our project's goal was to measure the sideways motion of Andromeda. The next image illustrates how we accomplished this goal. The box on the right shows Andromeda again, with the small box indicating the field we observed with Hubble. We observed this field on 2 occasions, one in 2002 and the other 7 years later. The background galaxies shown in the first blow-up are in fact so far away that they have no sideways motion, and therefore they serve as fixed beacons in the distance. By contrast, the Andromeda stars shift their positions over time due to the sideways motion of Andromeda, as illustrated in the second blow-up. So by measuring the relative shift of Andromeda stars with respect to the background galaxies, we were able to determine the sideways motion of Andromeda Galaxy. What made this project so challenging was that the shift is extremely small. But with sophisticated data analysis techniques we developed, we found that the motion can be measured with confidence. Ultimately, the location of Hubble Space Telescope above the Earth atmosphere made the measurement possible by providing the required image quality and stability. The next movie further illustrates our techniques. We start with the view of the night sky you saw before. If I can have the movie play, please. The Milky Way and Andromeda Galaxy are highlighted together with the visible constellations in this part of the sky. We now zoom into Andromeda and eventually to the small field we observed with Hubble. From the measured sideways motion, we projected the motion of stars into the future, as shown in the next animation. First, you see what the field looked like in 2002. And now we show an animation of how the field will change over a period of 30,000 years. This movie illustrates how the Andromeda stars move relative to the fuzzy distant galaxies in the background. Of course, our measurements were taken only 7 years apart, so the motion was a lot more difficult to detect than what the movie may suggest. So that concludes how we measure the sideways motion of Andromeda. Professor Wise will now describe some of the broader context of these results. Professor?
Okay, thank you, Dr. Sohn. Of course, we're fascinated by the future of our galaxy, the Milky Way galaxy, but these observations have added significance and importance because both the Milky Way and M31 are examples of the typical galaxy that we see around us today. And we'd like to know how the typical galaxy evolved, and we have 2 great examples nearby. If I could see my first slide, this is a wonderful picture taken by the Hubble Space Telescope. If you look at the large galaxies in this image, these are the ones that are nearby. And you can see that they are predominantly spiral disk galaxies like the Milky Way and M31. The smaller galaxies in this image are the ones that are more distant, much earlier stages of the expansion of the universe. Galaxies were much less regular at early times. We don't actually know why galaxies nearby us are predominantly disks, and we don't understand how disk galaxies evolve. And of course, that's one of the goals of modern astrophysics. The unique capabilities of the Hubble Space Telescope allow astronomers to tackle this problem in two complementary ways. One is to look at these small, distant systems and identify them at a range of times and try and see how the mix of galaxies types changes as a function of time. The other approach, which is the one taken by the astronomers we have here today, is instead to look at the end point, look at a large galaxy nearby, and try to identify the signatures of galaxy assembly. When we study galaxies with both techniques, they each tell us that mergers between galaxies happen, but we really want to know what were the systems that merged, when did they merge, and what was the consequence of that merger. By studying large samples of individual stars in both our galaxy and in M31, I mean, the stars are in separate galaxies, but for both of those galaxies, we have identified streams of stars which have been torn out of satellite galaxies, which have ventured on their orbits too close to the center of their parent galaxy. This is illustrated in my next slide, which is an artist's interpretation of some streams that have been detected about the Milky Way galaxy. So we've known for a while that galaxies, typical galaxies, disk galaxies, do evolve by snacking on small satellite galaxies. The importance of the research that we've just had presented is that the appetite of both the Milky Way and M31 has not been satisfied, and in fact, they're going to end up devouring each other. And when they do so, the Milky Way and M31 are going to join the pantheon of galaxies that we see in my next slide, which again is beautiful images from the Hubble Space Telescope of large colliding spiral galaxies. Small mergers with satellite galaxies, we call minor mergers, are quite common. The major mergers, those between galaxies of approximately equal mass, are much more profound for the system, can really change the morphological type, which is what one of the major goals is, to understand how does morphological type change. And the results that we've heard today, which have allowed the full three-dimensional motion of M31 to be measured for the first time, tell us that there will be a major merger between the Milky Way and M31. A much more profound statement, and I think it gives unique insight into how typical large galaxies evolve. Thank you. And I turn to Dr. Grunsfeld, who's going to, I hope, describe how he managed to allow Hubble Space Telescope to take these amazing images.
Well, the Hubble Space Telescope is this amazing machine that we've come to know and love over the past 22 years. When we think of the observations that Hubble has made that have been really, changed the world types of observations. They're observations that typically are looking back in time, looking back to the earliest moments of the universe to see the earliest galaxies, and they appear misshapen and irregular at these very high redshifts, looking back 13 billion years in history. And we study, back in history because it takes light a long time to travel to us. Edwin Hubble, of course, started this inquiry into what are these fuzzy objects that we now call galaxies. And so this has been a very long trek, if you will, to try and understand the history of the universe. And it's a very human story because we want to know about fundamental questions. Where did we come from? How did the universe form in the way that created galaxies, that created solar systems, that created Earths? And we think of astronomy very much in this historical context. A little bit of local history is Hubble was launched 22 years ago. We celebrated Hubble's 22nd birthday in April. Just 3 years ago, I was up on the Hubble Space Telescope, May of 2009, on Space Shuttle mission STS-125. That's why I'm wearing this jacket today, repairing an instrument called the Advanced Camera for Surveys. It had failed a few years earlier. but it was installed in 2002, another mission I had the privilege to fly on. And on that mission, we installed this incredible camera, the Advanced Camera for Surveys. And that's one of the resources that was used here. And it's because Hubble has been serviced by the Space Shuttle, that's why I'm wearing my Space Shuttle tie, that it was that longevity that allowed it to make these very sensitive measurements. It's just amazing that over just a 7-year span, this team has been able to record the proper motion, the tiny motion of the stars in Andromeda against the background sky, against background galaxies, that we were able to make this measurement. And in the meantime, that camera had failed. And it was a crew of astronauts, myself included, who went up and repaired the Advanced Camera for Surveys that enabled this work to be done. And I think the great thing about Hubble is in 2009 we did a Hubble complete makeover. We fixed the Space Telescope Imaging Spectrograph, the Advanced Camera for Surveys, put in the Cosmic Origin Spectrograph, did a whole host of repairs such that Hubble is now practically a brand new telescope. And so what's really exciting about the current measurements is it's not about historical astronomy. It's not about looking back in time, understanding the expansion of the universe. It's looking forward in time, which is another very human story. We like to know about our past. Where did we come from? We very much like to know where we're going. And so this, even though it's billions of years in the future, it gives us some portrait of what the night sky will look like, a really amazing event for whatever life exists on Earth at that time, of things that will transpire in the cosmos in the future. And I think that's a very exciting thing for Hubble to be doing. JD?
Thanks, John. And with that, we'll start our question and answer session. Because we have a large number of people joining us from a variety of locations, we'll need to limit reporters to one question and one follow-up. Once everyone has had a chance to ask a question, and if time permits, we'll go around for a second round. I ask that you identify yourself, your media affiliation, and then direct your question to a specific panelist to avoid any confusion. For those who would like to ask a question on the phone bridge, push the *1 keys on your telephone to be placed in the queue. And to use Twitter, send your questions to #AskNASA. And with that, let's get started. All right, we have Seth Bornstein here in headquarters.
Seth Bornstein, Associated Press. I guess for Roland, in terms of this merger here, you often have a bigger and a smaller actor. I know these are almost equal. In terms of the end result and the speeds, it's coming at 250,000 miles per hour. What's our relative speed to Andromeda? And is there sort of the two, is there one sort of the bigger brother, bigger, nastier, the bully in this crash, the truck in the crash, versus the car, and in terms of where the sun, obviously you said we'll survive. But are we going to be in a totally different place in terms of, right now we're on the edge. I mean, are we going to be so far out to the edge? Can you give us a little more detail about that?
So I will answer the first part of that question, and then I will pass the second part of that question on to my colleague, Dr. Besla. So the first part of your question was, who is the bigger player here? Well, that's a very good question. Andromeda and the Milky Way have long been known to sort of be twin galaxies. They're very similar in many ways. And we don't actually know which one of the two is more massive. So we think they're about as massive, but to within the uncertainties with which we know their masses, we don't actually know, and that continues to be debated by astronomers. And one of the things we had to do in our computer simulations is actually account for any uncertainties in the masses of these systems. Because once you have measured the velocity as we have, the future evolution is just determined by Newton's laws of physics. So you need to know the masses of the objects, you know their current velocities, you can figure out what's going to happen in the future. So in our simulations, we had to account for any uncertainties in those masses. But by and large, this is a merger of two roughly equal mass systems. Now, regarding the fate of the sun, I think Dr. Besla can take that question.
So within the simulations, what we do is we tag certain particles to be potential sun analogs. So these are particles that are sitting at roughly the right spot, location in our galaxy, and are moving at roughly the right speeds. And then we track what happens to them throughout the simulation. And what we find is that the vast majority of them are going to be at much larger distances than they are today. And so the most of them are going to be within, so the largest satellite of the Milky Way is the Large Magellanic Cloud. And so that's roughly what's, the distance between us and that galaxy is basically as far as the sun could potentially go. So it's not going to be lost to the system entirely. It'll still be part of this remnant galaxy in the end, but it certainly will be most likely much larger distances than it is today.
And a follow-up from Seth.
In terms of a follow-up, I guess the speeds, the speed and I guess the other part of the sideway motion that you determined here is how much more sideway motion would have been required for it to be a miss or a glancing blow?
Right. So in terms of the sideways motion, so let me first answer your first question. So the current approach velocity between these two galaxies is 250,000 miles per hour. But because they are attracting each other and they're falling towards each other, they're speeding up in the same way that something else that you drop towards the Earth will speed up. By the time they get more or less at their closest approach, they're about going at 5 times as fast as they're going now. So they'll be quite fast. In terms of the sideways motion, we have measured the sideways motion, but to within some precision, because it's a very hard measurement. We find that to within our precision, the sideways motion is smaller than about 1/3, 1/4 of the approach velocity. But the sideways motion will not actually change much with time. The approach velocity will get bigger and bigger because of the attraction, but the sideways motion will remain the same. So by the time they approach each other, the sideways motion is very much significantly less than the approach velocity. How much it would have taken for them not to merge is a bit of a complicated question because it depends on many assumptions you make in these computer models. But what we do know is that past understanding of our local universe indicated it would be unlikely for these galaxies to have a sideways motion of more than 200 kilometers per second, which is not quite the same units we're using before, but that's about twice as fast as the approach velocity. If in fact it had gone that fast, which might have been very well possible based on what we know about the local universe, probably they would not have merged, or it would have been way, 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 way into the future when many other things would have happened as well. If you integrate these things too far forward in time, there's all other sorts of other uncertainties that come in.
Thanks, Roland. We're moving now to a Twitter question from John Mason. How do you know that none of Andromeda's stars and planets will run into any of our stars and planets, including our own sun and Earth?
Shall I take this question?
Sure.
So we cannot rule out that some star in Andromeda may hit our sun, or that some planet in Andromeda, if there exists some, which may well be the case, may hit a planet in our own solar system. But these are very, very small objects, and there's a lot of space between them. So what we can say that the probability that this will happen is really, 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 really small, to the point that I would call it vanishingly small. So we can't really rule it out, but it would be a very unlikely event.
Okay, thanks, Roland. We're now going to the telephone bridge with Ian Thompson from the Register.
Hello. A question on a similar point. You said that the sun in 4 billion years' time will have used a fair amount of its fuel. What would the environment be like on Earth then, and would this change?
Can you repeat that question? Because it was very difficult to hear. You were breaking up.
Okay, sorry. In 4 billion years down the line, the sun would have changed a certain amount, of the environment of the Earth would have changed. You're saying this would have been unaffected by the collision?
Yeah, so let me expand on that a little bit. So our sun was born 5 billion years ago, and it has fuel left to perform nuclear fusion with for about another 6 billion years. So when Andromeda arrives, our sun will still be a regular star. And as such, we don't expect our solar system and the Earth's place in it will have changed very significantly. However, what we do know, and which I didn't mention before, is that due to the natural evolution of the sun, it'll get slightly hotter over time. And a few billion years from now, it'll actually have gotten sufficiently hotter to make life as we know it on Earth today impossible, because it would be too hot. But since we're talking billions of years into the future, I personally do not think that that necessarily means that our civilization will not be there. For example, if we find a smart way to use solar energy and turn it into air conditioning, we may still be able to live on this planet, even though our planet, by normal measures, would be too hot to live on. So the environment will change for other reasons as well, but by and large, when Andromeda gets here, our sun and its solar system will still be pretty much in the same state. There will be the same number of planets. They will be still going around more or less in circles. And, we can't rule out that other things may happen in the meantime, but I think by and large, that's not necessarily the expectation.
Thanks, Roland. We have a question here that probably John can answer. How much longer do you think we'll get service out of Hubble?
Well, the warranty was 5 years, so we still have 2 years on the crew warranty. But it's very hard to say because so few things have failed on Hubble to accumulate statistics so that we can predict how long Hubble will last. But I'm certainly hoping that we get another 6, 8, maybe even 10 years of life out of Hubble. There are things that we know will start failing eventually. Gyroscopes will start wearing out. Other things that have moving parts might start wearing out. But I'm very hopeful that we can keep Hubble going as long as possible.
Thanks, John. We're now going back to the telephone bridge with Mike Wall from space.com.
Oh yeah, do you guys have any idea, how many of these sorts of huge kind of galaxy crashes we have endured? The Milky Way has endured, and it's, 13, the kind of billion-year history or so. Is this something that is unprecedented for the Milky Way, or has this sort of thing happened before?
I think I'll take that. This is Professor Wise from Hopkins. We can actually trace the past major mergers in the Milky Way by looking at the kinematics of stars. And what we find is that this will indeed be unprecedented. We can trace the past major merger history because in a major merger, basically disks get destroyed. As you saw, you take two disk galaxies, smash them together, the orbital energy goes somewhere, and the main place the orbital energy goes into is to changing the orbits of the stars in the disks, putting them on much more energetic orbits, not nice circular orbits in the disk, changing them to three-dimensional orbits. When we look at stars in the disk of our galaxy, we can identify that there actually is a more energetic component of the disk, a thick disk. But basically, all the stars in the thick disk are very old. There has been ongoing star formation in the thin disk over the past 10, 12 billion years. If there had been a significant merger, it would have puffed up younger stars. So we can date the last significant merger that our galaxy has had by looking at the ages of stars that are not in the thin disk but have been puffed up into a thick disk. And because that age is old, it tells us that that's the time ago that there was a last significant merger. So the Milky Way has had probably quite a lot of small, minor mergers, but this major merger will be unprecedented.
Thanks, Rosemary. Once again, if you'd like to place a call on the telephone bridge, push the *1 key to get placed in the queue. We're back to the Twitter page right now. We have a question from Joseph's son. He's asking, what is the effect of the two black holes in relation to the merging of the galaxies?
Let me pass that question on to my colleague, Dr. Besla.
So definitely one of the most dramatic things that happens in collisions of galaxies is the two massive black holes in both of those galaxies will merge. And we've seen this in action. So we know that it's a very energetic event. But the thing is that with the Milky Way and Andromeda, these two black holes are not especially massive. And also there isn't a lot of gas around. So when black holes merge, it's an energetic event, but they also eat up a lot of gas. And that's what we really see in terms of the amount of energy that's produced. There isn't a lot of gas around in these galaxies, so we don't expect it to be extremely dramatic. But there will be a merger between these two massive black holes. It's unclear how much radiation will come out from that, for example, and whether that would affect our local environment. But it certainly should be a merger.
Can I follow up on that?
Sure.
So one thing to note is that the merger of the black holes, if and when that happens, will be very interesting in its own right. But the mass of these black holes is very small compared to the total mass of these galaxies. It's only of the order of, 1 part in 100,000 or so. So in terms of the overall orbits of these galaxies, the black holes have almost no influence. So they don't change anything we've said before, but they might add some interesting, sideshow in their own right that we haven't discussed here yet.
Thanks, Roland. back to the Twitter feeds here. Got a question from DagMT. During the merger, will some stars be permanently ejected into intergalactic space? If so, what fraction of the galaxy is lost?
Let me take that question. So in the simulations, as Dr. Besla discussed before, we did specifically look at particles like our sun to see what will happen to our sun. We find that in none of the simulations that we have run, it is possible for the sun to totally escape the gravitational pull of these two galaxies. So when Andromeda and the Milky Way merge, our sun will remain part of that galaxy. Our sun will move very far out, but it won't escape altogether. There is one interesting thing, though, is that we did look at this third galaxy, the Triangulum galaxy, which is a smaller companion of the Andromeda galaxy. It's about 10% of the mass of the Andromeda galaxy, and it essentially follows Andromeda through space. But because Andromeda is heading our way, the Triangulum galaxy is pulled with it and is also coming our way. We find that this Triangulum galaxy may actually hit us first. There is a 9% probability in our computations that the Triangulum galaxy M33 may hit us first. That won't have as much of an impact, but we may actually get a 1-2 punch of two galaxies hitting us in a row. Now, the other thing is that even if the galaxy M33 doesn't hit us first, there is actually a probability, significant, 20%, that at some point in the next 10 billion years, our sun will actually find itself inside of M33. So even though dynamically we'll still be part of the Milky Way Andromeda merger remnant, we might actually spatially find ourselves temporarily moving through this third galaxy before we then fall back towards the center of the merger remnant. So there's a lot of interesting things that can happen in terms of what may happen to the sun. And we have only modeled the three most massive galaxies in our local universe. The Milky Way and Andromeda dominate what is known as the local group of galaxies. And in that local group, there is actually about 50 galaxies. Most of them are much smaller, but 47 of those we haven't modeled. So some of these smaller galaxies may also, provide interesting things when this whole collision will occur. And there's certainly a lot of, opportunity here for further study to delve into those issues.
Thanks, Roland. Want to get another question from Twitter. Any plans of making Hubble redo the deep field experiment in different locations of space before it's decommissioned?
Well, the observations on Hubble are done on a competitive basis. So people propose, and we've just finished going through a proposal cycle. The proposals are reviewed and rated. But I know there are certain fields in space that have been studied in great detail, and there are folks who think we should redo the current deep field or other deep fields to look either further or in other areas. I think one of the more interesting questions that's folks are talking about now is we have the next Hubble 2.0, called the James Webb Space Telescope coming up. It's an infrared telescope. It will actually go where no Hubble has gone before, deeper into the universe, and be able to see lots of things that Hubble can't see because it's an infrared telescope. And while we still have Hubble, scientists are asking the question, are there things we should observe with Hubble now that we're going to want when we have James Webb Space Telescope in case Hubble doesn't last that long? And so that may be some other deep fields or some other kind of observations, perhaps even of Andromeda, that will help guide us in future science.
Okay, we have another question here. How can you predict with certainty, which you've mentioned several times, the actions that are so far into the future?
Well, so as I tried to mention before, calculating these things into the future isn't actually that complicated. So what you need is Newton's laws of motion, which have been known for hundreds of years and which students learn in high school. And with Newton's laws of motions, and you have two big things moving, you need to know only two things. You need to know their mass and you need to know their velocity. And we've measured their velocity and we've measured their mass. So it's a deterministic problem. You can just put those numbers in and you can solve it. Now, as it turns out, in our universe, most things happen on size scales and time scales that are just much bigger than our human perception normally allows. For us, 100,000 years sounds long, billions of years sounds so much longer that it's hard to grasp the difference. But the dynamics of this system of these two galaxies really isn't that different than many other dynamical systems we study. For example, the solar system, we have the Earth going around the sun once every year. It's been doing that for billions of years. We can calculate how this works. We understand it. We can calculate when we launch, rockets, when we launch spaceships. They basically are subject to the same laws of motion. We can figure out quite exactly how to do that. And these are all things one can calculate. The thing that's different here is that because these galaxies are bigger and they're more massive, things take a lot longer. But in terms of the underlying physics and the underlying equations of the problem, it's really no different. And we do know of many other things in the universe around us today, and there really isn't anything else around that is massive enough to perturb this. So it's not that we could have missed something major, because if there were some other galaxy that were 10 times as big as our Milky Way and Andromeda and close enough to perturb this, we would have known about it a long, long time ago. So I do think that this is a totally calculable problem once you know the masses and the velocities of these galaxies.
Thanks, Roland. Once again, the telephone lines are open. If you have a question, just push *1 on your phone. Back to the Twitter sphere here. Are there any similar mergers happening that we can today observe and perhaps learn from?
Well, perhaps I can take that one. I did show a montage of colliding galaxies. So we do know that there are ongoing, and there will be similar mergers between similar spiral galaxies. But as Roland was just pointing out, these mergers happen on extremely long timescales. So of course we can't actually watch them happening. What we can do is try to put together all these different snapshots in some kind of an evolutionary sequence so that we can understand which galaxies are just approaching, which ones have passed the center, which ones are coming back. This is ongoing research, but the merger that we now have predicted between M31 and the Milky Way is not that unusual. It's very unusual for each of those two galaxies, but in terms of what else is going on in the universe, it's not that unusual.
In fact, if you go on HubbleSite.org, you can find a whole collection of images similar to the montage that was shown earlier. And in fact, there's also some animations that will show you, examples of galaxies doing the dance, merging, and then the equivalent Hubble image, that compares to that particular animation.
Thanks, John.
I just wanted to follow up with that, just to kind of to specify why this particular observation is just so special. From a simulator's point of view, when we try and simulate these mergers of galaxies, what we find is that there's a huge error space in the velocities and the masses we choose. So this is an example of a way of simulating an upcoming merger where we actually know a lot of the parameters. We have very small error bars on the velocities. And this is what's so special about this observation, is that we now can actually simulate this with a degree of accuracy that we cannot do for any other interacting pair of galaxies.
Getting some excellent questions here on the Twitter feed. What are other ways that we are observing these movements other than Hubble?
You want to talk about that, Tony?
Well, yes, I'll take that question. There are some other programs that say these measuring the sideways motion of stars from the ground-based telescopes are. There are also like programs that using Hubble to actually measure proper sideways motion of other galaxies. But this project was the one that actually the accuracy of measuring the sideways motion have never been this actually good. So this has been the best accuracy we achieved with Hubble and with any other telescopes. So.
Yeah, and if I can just follow on that. As we've mentioned before, this is the first measurement of the sideways motion of Andromeda. There are other techniques to measure sideways motion that use radio observations. This does require that you have a radio source in this galaxy you can look at. But radio observations can yield very high positional accuracies because you can use what are called interferometric techniques. So you can use radio telescopes on different parts of our Earth and put the results together to make it look like you have a telescope almost the size of the whole Earth. So in a few years, it is likely that such measurement will become available for Andromeda, because just last year, for the first time, good radio sources were detected for which such measurements can be done. So likely in a couple of years, there will be other ways to look at this problem, which may refine this work and may provide further additional details, both on what might happen and also on the structure of the Andromeda galaxy. So this is definitely an ongoing field with different ways of looking at it.
Thanks, Roland. The next question we have is, could there be a quasar created?
Let me pass that one on to Gurtina.
Simulations that we ran, we didn't actually include any gas. And so we couldn't actually test specifically how much the black holes, when they merge and they form this one larger structure, how much gas they'll actually be eating. But this work has been done before. People have tried to simulate whether or not what would happen if the Milky Way and M31 collided, and in simulations with gas. And they found that there just isn't enough gas around to really fuel this black hole merger. And this is when we talk about active galaxies and we talk about quasars, we're talking about black holes that are very actively accreting gas. And so it's a very energetic event. And so that most likely will not happen with our Milky Way and M31 galaxies.
All right, thanks. We have another question here, and I think I know the answer, but I might be wrong. Once these two galaxies have collided, what's the new galaxy going to be called?
Well, so we haven't specifically tried to assign a name to this new galaxy, but there was a previous group that did calculations of what might happen under assumptions of the sideways motion. So before, no one had measurements, but that certainly didn't stop people from calculating what could happen if they were to be running into each other. And that particular group adopted the name Milkomeda as a mixture of Milky Way and Andromeda. Personally, I think I would like Lectomeda better, because if it's it's a more classical mix of terms and doesn't mix classical languages and Germanic languages. But I think one could name it various things, but I think ultimately we just call it the Milky Way Andromeda merger remnant, and as long as we all know what we're talking about, I think that there's no
Thanks,
confusion.
Roland. Could anything impede this collision?
Well, so I think I sort of touched on that earlier. So to solve the problem of the motion into the future, you need the velocities and you need the masses of these systems. So assuming we have in fact determined those correctly, the problem is quite deterministic, but what we haven't modeled is other bodies. So we have modeled these two galaxies and this third galaxy, the Triangulum galaxy M33, which we know are the three most massive galaxies in our local group of galaxies. So to significantly perturb this, you need something with a whole lot of gravity. And if there were something, and usually something with a whole lot of gravity is a galaxy. And all the galaxies have stars in them that we see. So we've mapped all the galaxies in the local universe. So we know what's out there. So we're pretty sure there isn't anything out there that is humongously massive that we might have missed. Now you might say, well, suppose there is something out there that is like a whole ball of dark matter, but there's no stars in it. That could actually be the case. And in fact, there was a lot of attention 10 or 20 years ago to a concept called the Great Attractor, which was a concentration of dark matter further away, not specifically affecting this, but it does illustrate the point that if there was a concentration of dark matter somewhere and you can't see it in terms of its light, you can actually notice it because that dark matter is going to affect the motions of other things around it. And those other things around it we can see and we can measure their motions, and we have measured their motions. So because people have done this over the past decades, we actually have a pretty good sense of the mass distribution of the local universe, even aside from our knowledge of where the galaxies are. And based on all of this work, which astronomers have pursued for many, many years, we don't really think there is anything out there that is both close and much more massive than these two galaxies. So based on that assessment, no, there is nothing that can perturb this. Of course, there's always a chance we may have missed something spectacular, but then that'll undoubtedly be a future topic for a press conference that will garner great attention, because it would be a wild surprise to all astronomers.
Thanks, Roland. I think we've got time for one more, but we will be able to continue this conversation at 3 p.m. with a web chat, and we'll give you the URL for that in just a few moments. I think the last question we've got here for the team is, when Andromeda comes, do we expect the local stellar neighborhood to be significantly more populated, i.e. more places to go?
Well, so that's a good question. So what we do know is that if you can define the solar neighborhood as the other stars that are around the sun and the gas. So once Andromeda arrives, we merge. We do know that there will be less gas in the solar neighborhood than there is now, because there will be less gas in general in this new galaxy. We also know that most likely, based on our simulations, the sun will find itself further out in this new galaxy. And the density, the number of stars in galaxies, drops with distance. So if that's true, the sun will find itself in a neighborhood that is less densely populated. It'll move from, say, from the suburbs to, downtown North Dakota. And, the neighborhood will be different. But we can't prove this. It is possible that the sun might actually move closer to the center of this new galaxy, or it might be on an orbit where it spends a lot of time at large radii, but then every now and then quickly plunges to the center. So there might be times when it finds itself very close to the center, where the density of stars is much higher. It might make an occasional visit to, say, Manhattan. And if it's really unlucky, it may actually get really, really close to the central black hole in the center of this merger remnant, and it could even be totally torn apart. But that is a likelihood that, again, I would call vanishingly small, but it's certainly one other interesting thing that one can speculate about that might happen as future events unfold.
Thanks, Roland. And that's going to have to do it for today's Hubble Media Telecon, or conference rather. I'd like to thank our panelists for joining us today. You're cordially invited to join us for a web chat to talk with our panelists at 3 p.m. Eastern by visiting the URL that's on the screen, and I'll read it to you real quick. http://go.nasa.gov/M31chat. For more information about this Hubble finding or more information about any of NASA's various projects, visit us on the web at www.nasa.gov or via any of the many social media venues such as Facebook, Google+, Twitter, and YouTube, and many more. Coming up next, a live SpaceX Dragon post-splashdown news conference at the top of the hour. Again, thanks for joining us and have a great day.